Welcome to our next lecture in the series on condensed matter theory. In the previous video we discussed the possibility to find bound states at the surface, and in order to make a bound state at the surface we made a model where we changed the potential at the surface. Now when you make the potential at the surface deep enough you will always find bound states. So that this can be a reason to find bound states is quite obvious. What I want to discuss in this video is if you can make a bound state at the surface without changing the surface potential. And actually just truncating the hopping that we have is not a small perturbation. So can this perturbation be so large that you're no longer in a perturbative regime and you get additional eigenstates in your system? And when you get additional eigenstates that are outside the continuum, then you know that the spectral weight of this state far away has to be zero, so you have to be bound close to the surface. Now in order to investigate this, we are going to use the Dyson equation, because I know that if I make an infinite sum and do a geometrical series, I will get my bare Green's functions of the infinite lattice, which have the poles that we have if you have no bound state, and then a term which is 1 over something, and when that diverges you will get additional bound states. So with the use of the Dyson equation I will be able to test what the conditions are that you need to get an additional bound state. And I will do this for a one-dimensional model as an example, just to get a feeling of what conditions we can have. And as a model I will take a single S-band on a one-dimensional lattice. We already know that this will not have a bound state, but at least I can devise the conditions that we need to solve in a very simple model. And then in the next video we'll have a look at an S and a P orbital, where we then can see which conditions. We can then use these conditions to test if we get bound states. And actually in the next video we will only do this numerically. A few weeks from now we'll also discuss the necessity to get surface bound states for some SP models without any surface potentials. Even if you would put in a repulsive surface potential you will get a bound state. Even if you put in an infinitely repulsive surface potential you will get a bound state somewhere. Most probably not at the infinite potential state, but then shortly below that. So, but that later. Now I'm just going to look at my one-dimensional tight binding Hamiltonian, which H0 is my infinite chain with an hopping as S sigma between side I plus 1 and I, and between side I and I plus 1, hopping to the left and to the right. So we have our chain and sides -2, -1, 0, 1, 2, 3, etc. Now I want to use the Dyson equation. So from an infinite lattice I want to go to a semi-infinite lattice. And I can do this if I define H1 as minus SS sigma A dagger minus 1 A0 plus A dagger 0 A minus 1. So H1 is basically cancelling the hopping between these two sides. We then have still a Hilbert space with sides on all lattices from minus infinite to plus infinite. But if you look at the local Green's function for positive sides, it just looks as if it is a semi-infinite chain, because there's no way you can move from one side to the other. So this we can use to calculate the Green's function of a semi-infinite chain with the use of the Dyson equation. And the Dyson equation is nice because it gives you clear conditions if you have a bound state or not, if you get additional poles compared to the infinite lattice or not. So we have our Green's function in real space for h0 plus h1. And this is given by the Green's function of the infinite lattice plus the sum over two auxiliary sides, g0, moving from z double prime to z. Then we have a scattering z triple, and we have the Green's function z triple z prime. So we move from z prime to z triple prime, we scatter from z triple prime to z prime, z double prime, and we move from z double prime to z. Now h1 has only a finite value for the combinations of z double prime and z triple prime of 0 and minus 1 or minus 1 and 0. So our Green's function is given by g0 z z prime omega plus g0 z0 omega psi 0 h1 psi minus 1 g minus 1 z prime omega plus g0 z minus 1 omega, and a scattering in the other direction. So I have my semi-infinite chain. I create a particle at z prime, I propagate to minus 1, I scatter from minus 1 to 0, and I propagate then in an infinite chain from 0 to z. Or I have my semi-infinite chain, I create my particle at z prime, I propagate to 0, I scatter from 0 to minus 1, and I propagate from minus 1 to z in the infinite chain. Now when z prime is larger or equal than 0, then I know that g minus 1 z prime of omega is 0. If I create my particle on this side and I have no hopping between 0 and minus 1, I can never propagate to a negative side. So my full Green's function is given by g0 plus g0 z minus 1 omega. g0 you can of course propagate also through negative to positive or positive to negative numbers. Phi minus 1 h1 phi 0 g0 z prime of omega. This leaves us with an infinite series, because we can replace the full Green's function again with the Dyson equation, plus g0 z minus 1 omega, and then we have a sum of 0 to infinite, where we can scatter h1 phi 0 n plus 1 times. We have a propagator between side minus 1 and 0, n times, and a propagator g0 from z prime to omega. So in our infinite chain we create a particle at z prime, we propagate to 0, which is on the right side of the impurity. Then you propagate from -1 to 0, you scatter from 0 to -1, you repeat this infinitely times, or you change the orders here. You propagate from z prime to 0, you scatter from 0 to -1, you propagate from -1 to 0, you scatter from 0 to -1, you do this n times and you sum over all possible amounts. You can do this 0, 1, 2 up to infinite times, and then you propagate from -1 to z. And that gives you the full Green's function, where you broke the bond between 0 and -1. Now this is a geometrical series. G0, Z, Z prime omega. We nicely assume that our Green's functions are analytical, such that we can do analytical continuation in this infinite sum. G0, Z minus 1 omega, phi minus 1, H1, phi 0, G0, 0, Z prime of omega, 1 minus, phi minus 1, H1, phi 0, G0, 0, minus 1 omega. So we changed this, we did the geometrical summation there. So we get an extra pole, which is a bound state. If 1 over 1 minus H1 phi 0 G0 0 minus 1 omega diverges. Now for the case of a one-dimensional chain with a single s orbital, we know that the hopping is negative, the Green's function is always negative, and there is no solution to this equation. There is no way to make the denominator 0. That will become different if we look at different models. And especially if you look at models where you have more than one band per unit cell. Either more than one atom or more than one orbital per atom. In that case, of course, these are no longer complex numbers, but they become matrices. So we look here at a matrix inversion, and we have to look when that matrix inversion is singular. The moment that your matrix inversion is singular, you will get additional poles. And you will get that independently from surface potentials that you might have in your system. So just by the bare fact that you break the translation symmetry, you stop the hopping, that can be such a large perturbation that you get additional bound states at the surface. And in our next video we'll show this in an example where we have an S and a P shell, so 4 orbitals on a cubic lattice, where you will get additional surface states without having to change any of the on-site potentials. For now, thank you very much for your attention. We see each other later. Stay healthy.